Settle in for this one. Pour yourself something warm and get comfortable, because what I am about to show you has broken the confidence of every physicist who has stared at it long enough. There is an experiment so simple a student can run it in an afternoon, yet its result suggests a particle does not decide what it is until something looks. Not a person, not a mind, something stranger, and nobody agrees what. For the next while we will sit with that honestly. No mysticism, just the real unsolved crack at the center of reality. If questions like this keep you up at night, subscribe and tell me where you are watching from and what time it is. Let us begin with something almost insultingly simple: a wall. A flat barrier standing upright, and cut into that barrier are two narrow vertical openings, side by side, close together. Behind the wall, at some distance, stands a screen. That is the entire apparatus. No glowing reactor, no mile of tunnel buried under a mountain. Just a wall with two openings and a screen to catch whatever comes through. Hold that picture in your mind, because we are going to return to it again and again, and by the time we are finished, it will look like the most unsettling object you have ever imagined. First, let us do the version that makes perfect sense. Imagine you have a machine that throws tiny marbles, one after another, in the rough direction of the wall. The marbles scatter a little. Some sail through the left opening, some sail through the right opening. Most hit the wall and stop. The ones that make it through travel on and strike the screen. And where they strike, they leave a small mark. What pattern do you expect to build up over time? Think about it for a moment before I say it. You expect two stripes. A little pile of marks lined up behind the left slit, and a little pile of marks lined up behind the right slit. The marbles that went through the left opening land in the left band. The marbles that went through the right opening land in the right band. Two bands, two slits. Clean, obvious. This is how objects behave. A thing goes through one opening or the other, and it lands behind the one it went through. Now set the marbles aside and think about waves instead. Picture a calm pool of water, and you tap the surface rhythmically so ripples roll outward toward our wall. The ripples reach the two openings, and here something different happens. Each opening becomes a new source of ripples on the far side. Two fresh sets of ripples spread out from the two slits, and they begin to overlap. Where the crest of one ripple meets the crest of the other, they add together and make a taller crest. Where a crest meets a trough, they cancel, and the water goes flat and still. This adding and cancelling is called interference, and it is the unmistakable signature of a wave. It is the thing waves do that solid objects cannot. So, along the screen you no longer see two simple bands. You see a whole series of stripes. A bright band where the ripples reinforce, then a dead zone where they cancel, then bright again, then dead again, fanning out across the screen. Physicists call this an interference pattern, and for 200 years it has been the reliable fingerprint that tells you with certainty that whatever passed through those slits was a wave. Two bands means particles. Many bands means waves. That was the rule. That was settled. Let that distinction sit for a moment, because everything that follows is going to take that clean, comfortable rule and quietly tear it in half. Now we make one change. We stop throwing marbles and stop tapping water. Instead, we use electrons. An electron is a particle of matter. It is one of the building blocks of every atom in your body, in this room, in the screen you are watching me on. It has a definite mass. It carries a definite electric charge. When one strikes a detector, it arrives as a single, countable hit in one place, like a marble landing, never smeared across a region like a wave. By every test we can run on a single one of them, an electron is a particle, a tiny, indivisible piece of stuff. So we build a gun that fires electrons at our wall with 2 slits, and we put a detecting screen behind it that lights up with a small dot wherever an electron lands. We expect, naturally, the marble result. 2 bands. The electrons that go through the left slit pile up on the left. The electrons that go through the right slit pile up on the right. Particles go through one opening or the other. We have known this since we were children stacking blocks. We turn the gun on, and the electrons start to arrive. At first the screen looks random, a dot here, a dot there. Each electron lands as a single sharp point, exactly as a particle should, one clean hit at a time. There is nothing wave-like about any individual arrival. Each one is a definite mark in a definite place. So far, the marble picture is holding perfectly, but we are patient. We let the gun run. Hundreds of electrons, then thousands, then tens of thousands of individual dots, each one a particle, each one landing alone. And slowly, out of all those separate hits, a shape begins to emerge on the screen. It is not 2 bands. It is many bands. Bright stripe, empty gap, bright stripe, empty gap, fanning across the screen. It is the interference pattern. It is the fingerprint of a wave. The exact pattern the ripples in the pool made. The pattern that is supposed to be impossible for particles. Sit with how strange that already is. We fired hard little pieces of matter, one at a time, each landing as a single point, and collectively they arranged themselves into the signature of a wave. Somehow, on the way from the gun to the screen, each electron behaved as though it were spread out like a ripple, passing through both slits at once and interfering with itself, before snapping back into a single point at the moment it landed. It helps to know that this rule, 2 bands for particles and many bands for waves, was not some fragile laboratory curiosity. It was bedrock. Back at the very start of the 1800s, a physician and polymath named Thomas Young shone light through 2 slits and watched the bands of brightness and darkness fan across a surface. And that single demonstration settled an argument that had run for over a century. Isaac Newton himself had believed light was made of tiny corpuscles, little particles streaming from a source. Young's stripes seemed to prove him wrong, because only waves make that pattern. Only waves add and cancel. For 100 years afterward, the interference pattern was treated as the courtroom evidence that closed the case. If you saw those stripes, you were looking at a wave, and there was nothing more to discuss. That is the weight of the rule we are about to watch shatter. This is not a small expectation being gently revised. This is 2 centuries of certainty, walking confidently into a room and being quietly undone. And I should tell you, so the strangeness lands with full force. That light does the very same thing the electron does. Turn the brightness of a lamp down far enough, and light arrives not as a smooth flow, but as individual packets, single photons, one indivisible arrival at a time, each landing as a single point, exactly like a particle. So you can run our experiment with light too, one lonely photon at a time, and the interference pattern still builds. Dot by patient dot. Newton was not simply wrong, and Young was not simply right. They were each holding one half of a thing that refuses to be only one or the other. Light is granular like a particle when it lands, and spread like a wave when it travels. And matter, we are about to confirm, is exactly the same. The divide we drew between waves and particles, the divide that organized physics for generations, turns out to be a line the universe never agreed to honor. There is a reason we do not notice any of this in daily life, and it is worth a moment, because it tells you why the mystery hides. Everything has a wavelength, a measure of how spread out its wave nature is, and for anything larger than a speck of dust, that wavelength is so unimaginably tiny that the wave behavior is buried far below anything you could ever detect. A thrown baseball has a wavelength so small that no slit narrow enough to reveal it could ever be built. You are made of waves too, in this sense, but your wavelength is so vanishingly small that you will never diffract, never interfere, never shimmer. The quantum strangeness does not switch off as things get bigger. It just shrinks below the threshold of the visible, drowned out, hidden in plain sight. Only when we go down to the electron, to the photon, to the very small, does the wave nature swell up large enough to leave its fingerprint on a screen. The wall with two slits is a magnifying glass, held over a feature of reality that is present everywhere and noticed almost nowhere. Maybe you have an objection already, and it is a good one. Perhaps the electrons are crowding each other. Perhaps they are bumping and jostling on the way through, like a crowd squeezing through two doors, and all that bumping somehow stirs up the wave-like pattern. It is a reasonable thought. So the experimenters did the obvious thing to rule it out. They turned the gun down, way down, so low that only one single electron is in flight at any moment. One electron leaves the gun. It crosses the gap. It lands. Then, and only then, the next electron is released. There is never more than one electron in the whole apparatus at the same time. Each one travels completely alone, with nothing else to bump into, nothing to interfere with, no crowd, no neighbor, nothing, and the pattern still builds. Slowly, dot by lonely dot, over hours, the interference stripes appear again. Each electron lands as a single point with no idea, it would seem, of where the others have gone or will go. Yet the accumulation of all those isolated, solitary arrivals is once again the unmistakable pattern of a wave. Let that land properly, because this is the heart of it, and it is worth slowing all the way down. A single electron, utterly alone in the apparatus, with nothing to interfere with, still produces, over many runs, the pattern that can only come from something passing through both slits at once and overlapping with itself on the far side. The only thing each electron could possibly be interfering with is itself. What does that even mean? A single particle, a thing we are confident is one indivisible piece of matter, leaves the gun. To make the interference pattern, it must, in some sense, go through both slits. Not the left one or the right one, both, at the same time, and then on the far side, the two versions of its own journey overlap and interfere, reinforcing in some places, cancelling in others, which decides where it is allowed to land. and then it lands as one dot in one place. If you find that hard to picture, that is not a failure of your imagination. It is genuinely not picturable in the ordinary sense. There is no little movie you can run in your head of an electron splitting in two, sliding through both gaps and reassembling, that survives close inspection. The mathematics does not describe the electron taking a hidden path we simply failed to watch. It describes something else entirely, a spread-out wave of possibility that covers both slits, and we will come to what that actually is in time. For now, just hold the brute fact, because here is the obvious next move, the move anyone would make. We want to catch it in the act. We do not believe the electron really goes through both slits, so we decide to simply look. We will watch the slits. We will place a small detector right at the openings, something that can tell us which slit each electron actually passes through, and then we will have our answer. Either it goes through the left, or it goes through the right. And this talk of both will dissolve the moment we actually check. That experiment has been done, and what it reveals is so strange that it took the better part of a century and is, to this day, not understood. But I am going to make you wait for it. I am going to make you sit on the edge of that question, because the answer deserves its own chapter and its own careful telling, and rushing it would cheapen the strangest single result in the history of science. For now, I want you to feel the size of the problem we have already uncovered with nothing more than a wall, two slits, and a screen. We brought two pictures of reality to this experiment. In the first picture, the electron is a particle, a marble, a definite thing that goes through one opening and lands in one of two bands. In the second picture, the electron is a wave, a ripple that goes through both openings and makes many bands. The trouble is that the electron refuses to commit to either picture. When it lands, it is a particle, a single point. When it travels, it behaves like a wave, spread across both paths. It is as if the question is the wrong question, as if reality at this scale simply is not built from things that are either one or the other. There is one more layer of strangeness hiding in how the pattern forms, and it deserves a moment of its own. Watch a single electron land, and you cannot predict where it will go, not even in principle, as far as anyone can tell. The theory does not say this electron will land here. It says only that, across many electrons, a certain fraction will land in this band and a certain fraction in that one. The individual arrival is genuinely unpredictable, while the collective pattern is rigidly, beautifully precise. Each dot is a surprise. The portrait the dots paint is fixed to the last detail. That combination, perfect order built out of perfect individual randomness, is itself something we never see in the ordinary world, and it is woven into the foundation of everything. The universe at this scale does not deal in certainties about single events. It deals in flawless certainties about crowds of events, while leaving each member of the crowd free, unpredictable, undetermined, until it lands. Hold that, alongside everything else, because it is part of the texture of what we are uncovering. There is a temptation here, and I want to name it so we can set it gently aside. The temptation is to reach for the mystical, to say the electron is magic, or that it knows, or that the universe is playing tricks. We are not going to do that. Not because the truth is comfortable, but because the truth is strange enough on its own that it needs no decoration. Every claim I make in this video is something you could check, something written in textbooks, something that working physicists agree happens. The mystery is not that the data are unclear. The data are crystal clear and have been reproduced thousands of times in laboratories all over the world. The mystery is that nobody can agree on what the data mean. That is a very different and much deeper kind of not knowing. So let me leave you, at the close of this first part, with the picture exactly as it stands. Imagine that lonely electron leaving the gun. It is one thing, one particle, by every direct test we can perform. It crosses toward a wall with two narrow openings, and on the far side, the screen records, over thousands of patient repetitions, a pattern that can only be made by something that went through both openings at once and interfered with itself along the way. The particle that is one thing somehow explores two paths. The piece of matter that lands in a single point somehow traveled as a spread-out possibility, and we have not even touched the detector yet. We have not yet tried to watch. When we do, in the next part, the electron is going to do something that should not be allowed. It is going to notice. Not notice the way you or I notice, but respond instantly and reliably to whether or not information about its path exists in the world. The mere availability of an answer to the question which slit will change what the electron does, will erase the wave, will restore the marble. Keep the wall in your mind. Keep the two slits. Keep that single, solitary electron, suspended in flight. Somehow everywhere it is allowed to be at once. We are going to walk straight into the thing that breaks the picture, and we are going to do it slowly and honestly and all the way to the bottom. We left an electron in flight, suspended between two slits, behaving as though it traveled through both, and we made a promise. We said we would catch it in the act. We would place a detector at the openings, watch which slit each electron passed through, and put this nonsense to rest. So let us keep that promise now, slowly, because what happens next is the moment the floor gives way. The setup is exactly as before. The same gun, turned down so low that only one electron is ever in flight. The same wall with two slits. The same screen behind it that records each landing as a single dot. The only thing we add is a way to know. We install a small detector at each slit, an instrument that registers when an electron passes through it, so that for every single electron we can say, with certainty, left or right, nothing else changes. Same gun, same slits, same screen, same distances. We have added only knowledge, only the answer to one question: which way did it go? We turn it on. The electrons fire, one at a time, alone, just as before, and our detectors do their job beautifully. Every electron registers at exactly one slit: left, right, right, left, never both. Each one passes cleanly through a single opening, like a marble, like a sensible piece of matter, and our instruments record an unbroken list of definite answers. Good. This is what we wanted. The electron is a particle after all, and it goes through one slit. And now we will look at the screen and see the interference pattern built by particles that each took a definite path. We look at the screen, the interference pattern is gone. In its place are two bands, the marble pattern, the boring, sensible, expected pattern of objects that each went through one opening and landed behind it. The stripes have vanished completely. The wave is gone. By doing nothing more than installing detectors that tell us which slit each electron used, we have changed the result. The electrons stopped behaving like waves the moment their path became known. Let that sit, because the instinct to explain it away is going to be very strong, and we are going to resist every cheap version of the explanation until only the real strangeness is left. Now we do the cleanest test imaginable. We leave everything physically in place, and we simply switch the detectors off. We do not remove them, we do not touch the apparatus. We just stop them from recording. We stop gathering the information about which slit. Same gun, same slits, same screen. The detectors are still sitting there, but now they tell us nothing. The interference pattern comes back. Turn the detectors on, the wave dies, and two bands appear. Turn them off, the wave returns, and the stripes come back. On, off, particle, wave. We can do this all day. The single thing that decides whether the electron behaves like a spread-out wave or a definite particle is whether the information about its path is available in the world, not how hard we push it, not how much energy we use, the availability of the answer. That is the lever. That is the thing that flips reality from one face to the other. Now I want to be extremely careful here, because this is the exact spot where the honest mystery gets buried under a mountain of nonsense, and I refuse to do that to you. The tempting story, the one you have probably heard, is that the electron knows it is being watched. That consciousness reaches out and collapses it. That the universe somehow cares about your attention, your awareness, your human gaze. Pour yourself a little more of whatever you are drinking. Get comfortable, because I am going to take that story away from you, and then I am going to show you that what is left is stranger than the story we are throwing out. Here is why it is not about consciousness. To detect which slit an electron went through, you have to physically interact with it. You have to bounce something off it, or let it disturb a field, or absorb a tiny piece of light that scattered from it. There is no way to learn the path without some physical interaction touching the electron and carrying the information away. And it turns out that this physical interaction, this entangling of the electron with the rest of the world, is what destroys the interference, not your mind, not your eyes. The plain physical fact that the electron got tangled up with something else, something that now holds a record of where it went. You can prove this is not about a conscious observer. The detector can record the witch slit information onto a device, store it on a hard drive, and let it sit there with no human ever looking at it. The interference still vanishes. No mind ever read the result, yet the wave still died. The pattern does not wait for a person. It responds to whether the information physically exists somewhere in the universe, recorded, in principle knowable. The moment the electron's path is written into the world, written into anything, the wave is gone, whether or not a single living being ever checks the record. So strip away the mysticism, and here is the clean, brutal statement of the puzzle. It is not about consciousness, it is about information. When the world contains a fact about which slit the electron used, the electron behaves like a particle. When the world contains no such fact, when the path is genuinely unknown and unknowable even in principle, the electron behaves like a wave and interferes with itself. The presence or absence of an answer, somewhere, anywhere, in the physical fabric of things, decides what reality does. Dwell for a moment on the reversibility, because it is the cleanest proof that something profound is going on. We are not breaking the electron when we measure it. We are not damaging it, not roughing it up so badly that it forgets how to be a wave. We know this because the instant we stop recording the path, The wave comes straight back, perfect, undiminished, as if nothing had happened. Flip the recording on, the wave is gone. Flip it off, the wave returns. On, off, and reality obediently switches between two utterly different faces, tracking nothing about us except whether an answer to one question is being written into the world. If measurement were simply a violent disturbance, you could not undo it by merely choosing not to keep the record. The fact that the wave returns the moment the information stops existing tells you the lever is the information itself, not any force we apply. That is as close as physics comes to a finger, pointing directly at the thing we do not understand. Whatever a measurement is, it is bound up with the existence of an answer, and the existence of an answer is something we can switch on and off, and reality follows the switch. That is the observer effect, honestly stated, and notice that it has nothing to do with observers in the everyday sense. A better name would be the entanglement effect or the information effect. To observe always means to interact, and to interact always means to entangle, and to entangle means the world now holds a record. That record is the thing that matters. Now let me give you the mathematical creature that sits underneath all of this, because we cannot keep circling the strangeness without naming it. The name is superposition. In quantum mechanics, we do not describe the electron by saying it is at a particular place going in a particular direction. We describe it by something called a wave function, which is, very roughly, a map of all the possibilities at once and how they relate to one another. When the electron approaches the two slits, and we have no way to know its path, its wave function passes through both slits. Not in the sense that the electron is secretly in two places and we just cannot see it. In the sense that the complete physical description of the electron genuinely includes both paths, woven together, each able to add to or cancel the other. That woven together state of both at once is a superposition. Let me try to bring that to human scale, knowing that every analogy here leaks. Imagine a coin spinning in the air. While it spins, you might say, it is neither heads nor tails. It is some blur of both, and only when it lands and you look does it become one. That is the popular image of superposition, and it is not quite right, but hold on to the part that is useful. A superposition is not the electron being secretly one thing while we remain ignorant. It is a real physical state in which the alternatives coexist and influence each other, and that mutual influence, that interference between the possibilities, is something we can actually measure on the screen. The stripes are the fingerprint of the possibilities overlapping. You cannot get interference from a coin that is secretly already heads. You only get it from genuine both at once. And here is the turn of the screw. The moment any part of the world records which path the electron took, the superposition is broken. The two possibilities can no longer overlap and interfere because they have become entangled with something else, the detector, the hard drive, the stray photon that bounced away carrying the news. The interference disappears not because the electron was forced into a slit by a rough touch, but because the two strands of possibility got tied to different states of the outside world and can no longer reach each other to cancel and reinforce. The wave does not so much die as it gets diluted into the rest of reality, spread so thin across the detector and the room and everything it touched that we can never gather it back. Let me press on the coin image a little more, because the place where it breaks is exactly the place where the truth lives. With a spinning coin, you feel certain that at every instant it really is either heads or tails, that the blur is just your eyes failing to keep up, that underneath the blur there is a definite face pointing up at all times and you simply cannot see it fast enough. If that were how the electron worked, if it secretly went through one slit and we were merely ignorant of which, then there would be no interference. The stripes could never form. A thing that is secretly already committed to one path cannot overlap with a path it did not take. The interference pattern is the hard, measurable proof that the electron is not secretly one thing we failed to observe. It is genuine both, genuinely overlapping, genuinely interfering with the version of itself that went the other way. The coin is a lie we tell ourselves to stay comfortable, and the screen calls the lie every single time the stripes appear. This is the thing that broke so many great minds, and I want to honor how hard they fought it. Einstein spent the last decades of his life convinced that there had to be a hidden layer underneath, some set of definite properties the electron carried all along that the theory simply failed to describe, so that the randomness and the both at once were only our ignorance of deeper machinery. He was one of the most powerful minds our species has produced, and he could not accept that the world was built this way. And the remarkable thing, the thing we will come back to, is that the question of whether there is such a hidden layer was eventually turned from philosophy into experiment. The experiments were done, and the simplest, most comforting version of Einstein's hope did not survive them. The universe really does seem to withhold the answer until it is forced to give one, not because the answer is hidden, but because, in some sense, we still cannot fully put into words. The answer is not there to be hidden until the world demands it. Let me also clear away a second comforting story before it takes root, because people reach for it the moment they hear that detecting the electron disturbs it. The story goes like this. To see the electron, you have to hit it with something, a photon, a probe, and that hit knocks it off course, and the knock is what smears out the interference. It sounds reasonable. It sounds almost obvious. But it is not the real explanation, and we know it is not, because experiments have been designed where the witch slit information is gathered so gently, with such a feather-light interaction, that the physical disturbance to the electron is far too small to wash out the pattern by brute force. And still the pattern vanishes. The wave dies not from the violence of the measurement, but from the mere fact that the information now exists. You can make the touch as soft as you like. As long as the world ends up holding the answer to which slit, the stripes are gone. It is the knowing, not the bumping, that matters. That is the result that should make you sit very still. And now the deepest version of the question rises into view, the one this whole video is built around. What, precisely, counts as a measurement? The detector is made of atoms. Those atoms obey quantum mechanics. The hard drive is made of atoms. The room is made of atoms. You are made of atoms. If everything is quantum, if everything can in principle be in superposition, then what is it about the detector that breaks the spell? Where exactly is the line between the quantum world, where possibilities overlap and interfere, and the ordinary world, where things are simply one way? Why does the electron get to be both, but the detector that records it does not? What is so special about the act we keep calling looking? Notice that nobody slipped a definition of measurement into the equations. The mathematics of quantum mechanics describes the smooth flow of the wave function exquisitely well. It does not tell you when a measurement happens, what qualifies as one, or why measurement produces a single definite outcome instead of yet another superposition. We put that in by hand. We say, here, at this point, a measurement occurred, and now the electron is definitely in the left band. But the theory itself never says where here is. That missing line, that undefined boundary between the world that shimmers with possibility and the world that simply is called the measurement problem, and it is the crack at the center of physics. We are not going to solve it tonight. Nobody has solved it in 100 years. But we are going to walk all the way around its edges. And the next step is the experiment that makes the timing of it all genuinely disturbing. Because so far you might still be telling yourself a quiet, comforting story. You might be thinking that the electron on its way to the slits somehow senses whether the detector is on and adjusts its behavior in advance, as if it checks the conditions at the start of its journey and decides then whether to be a wave or a particle. In the next part, we are going to destroy that comfort too. We are going to delay the decision. We are going to wait until the electron has already passed the slits, already finished its journey, already in some versions landed, and only then choose whether or not to learn its path. And the universe, somehow, will still give the consistent answer. Keep the wall in your mind. Keep the detectors on and off, wave and particle. We are about to start playing with time. So far, you have a story you can almost live with. The electron, somewhere near the slits, responds to whether its path can be known. Uncomfortable, yes, but at least the response happens there, at the slits, in the moment of passage. You can imagine the electron arriving at the wall, sensing the situation, and choosing its behavior on the spot. It is not a good explanation, but it lets you keep cause before effect. The looking comes first, then the electron behaves. Hold on to that comfort for just a little longer, because we are about to take it apart. To do that, we need one more ingredient, and it is the strangest ingredient in all of physics. It is called entanglement. Here is what you need to know about it. There is a process that can take a single particle and convert it into two particles that fly off in different directions, and these two particles are born linked. Their properties are tied together in a way that has no everyday equivalent. If you measure one and find a certain result, the other is instantly committed to the matching result, no matter how far apart they have drifted. They are not two separate things that happen to agree. They are described by a single shared state. Einstein hated this. He called it spooky action at a distance, because it looked to him like one particle reaching across space to touch the other. We now know entanglement is real, tested to exhaustion, and woven into the fabric of how the world works. For tonight, the only thing you need is this. We can make pairs of particles that carry shared information, so that learning something about one tells us something about the other. Now we rebuild our experiment around this idea, and this is the setup that has caused more sleepless nights than almost any other in modern physics. It is called the delayed choice quantum eraser. Let me walk it slowly, because the power of it is entirely in the details and the timing. We send particles of light, photons, toward our familiar wall with two slits. But just after each photon passes the slits, We run it through a special crystal that splits it into a pair of entangled photons. Now we have two photons born from the original, carrying shared information about which slit the parent came through. We call one of them the signal photon. It travels on toward a screen, the same kind of screen we have used all along, where its landing position is recorded. We call the other one the idler photon, and we send it on a separate, longer journey through a maze of mirrors and beam splitters that we have designed very carefully. Here is the heart of the design. That maze for the idler photon can do one of two things, and we get to choose which. In one arrangement, the idler photon ends up at a detector that reveals which slit the original came through. The path information is preserved, written into the world, knowable. In the other arrangement, the maze deliberately mixes the possibilities so thoroughly that by the time the idler photon lands, it is impossible, even in principle, to tell which slit the original used. The path information is erased, gone, wiped from the universe. You already know, from everything we have built so far, what this means for the signal photon. If the world ends up holding the which slit information, the signal photons form two bands, the particle pattern. If the world erases the which slit information, the signal photons form interference stripes, the wave pattern. Knowledge kills the wave, erasure restores it. We have seen this. It is consistent with everything in part 2. But now comes the move that breaks time. We make the idler photon's path much longer than the signal photons. We arrange the distances so that the signal photon reaches its screen and is recorded first. It lands. It leaves its dot. Its journey is over. The data is collected. Done. And only afterward, only after the signal photon has already arrived and been recorded, does the idler photon finish crawling through its long maze and meet its fate, where we decide, or where a random switch decides, whether to preserve the path information or erase it. Read that again, and feel the order of events. The signal photon lands before the choice is made about whether its partner's information will be kept or erased. The thing that should determine whether the signal photon behaved as a wave or a particle has not happened yet when the signal photon already finished behaving. So what do we find? We find that the signal photons that landed before the erasure choose to form an interference pattern every single time the idler's information was later erased. And the signal photons, whose partners later revealed the path, form two bands. Every single time, the pattern on the screen matches the choice that was made after those photons had already landed. The behavior lines up with a decision that came later in time. Let that land properly, because the temptation now is to scream that the past has been rewritten, that the later choice reached backward through time and changed what the photon did. That is the headline you have seen. The universe edits its own history. The future controls the past. It is thrilling, and it is wrong. And I promised you honesty, so let me show you exactly where the trick lives. Because the honest version is still strange enough to keep you up at night. Here is the crucial detail that the breathless version always hides. If you look at the full pile of signal photons all together, the ones whose partners were erased and the ones whose partners were revealed, all mixed into one heap, you see no interference pattern at all. Just a smooth blob, no stripes. The total picture on the screen never shows the wave. It looks ordinary no matter what you do later. The interference only appears when you sort the signal photons afterward, separating them according to what happened to their idler partners. You take the signal photons, whose idlers landed in the erasing detector, and you plot only those, and there, in that subset, the stripes appear. You take the signal photons whose idlers revealed the path, and you plot only those, and they form the particle pattern. The wave was hidden inside the data all along, but you can only pull it out by using the information from the idler, the information that arrives later. Do you see what that means? Nothing about the screen changes when you make the later choice. The signal photons landed where they landed. Those dots are fixed, and were always fixed. What the later choice changes is which dots you are allowed to group together to reveal a pattern. The future does not reach back and move any photon. It only determines how you are permitted to sort what already happened. To actually see the interference, you need both pieces of information, the signal landing and the idler outcome, and the idler outcome travels at the speed of light like everything else. You can never use this to send a signal backward in time, never learn anything before it is knowable, never change a single dot that already landed. The arrow of time survives. Cause still comes before effect in every way you could ever cash out. So breathe. The past is not edited. Take that small mercy, and yet sit with what remains, because it is not small. What remains is this. The universe steadfastly refuses to let you have both the path and the wave at the same time, no matter how you arrange the timing, no matter how you try to sneak the question in after the fact. You cannot trick it. You cannot set things up so that the photon commits to a single slit and also builds the interference pattern. Every time you find a way that information about the path could exist, even information locked in a particle still in flight, even information you have not looked at yet, even information whose fate is not decided until later, the wave quietly withdraws. And every time you genuinely erase that information, make it truly unrecoverable, the wave returns, threaded invisibly through data that already landed. It is as if reality keeps perfect books. It will not allow a contradiction to appear. It will not let the world hold both a definite answer to which slit and the overlapping possibilities that only exist when there is no answer. The consistency is absolute, and it is maintained across space and across time and across the long delay of the idler's journey. Somehow the whole arrangement, the signal and the idler and the maze and the screen, behaves as a single connected situation, not a sequence of separate local events, and the books always balance. I want to slow all the way down on the part that does the real work, because this is where careful thinking saves you from a century of bad headlines. Picture the two piles of data we end up with. There is the screen full of signal photon dots, fixed in place, recorded and finished. And there is the separate record of where each idler photon went and what happened to it. The magic word that everyone misuses is correlation. The signal dots, taken alone, are a shapeless smear. The idler outcomes, taken alone, are just a list. It is only when you lay the two records side by side and connect each signal dot to the fate of its own idler partner that structure emerges. Sort the dots by their partner's fate, and the hidden stripes step out of the smear. Without that second record, the stripes are invisible, and that second record cannot reach you any faster than light can carry it. That is the whole reason no message ever travels backward in time here. The pattern was always latent in the dots, but you need the key, and the key arrives the slow, honest way. like everything else. Think of it like this. Imagine a deck of cards already dealt face down across a table. Fixed, unchangeable, the deal already done. Later, someone hands you a rule for sorting those cards into 2 stacks, and only after you sort them does a pattern in the colors become visible. The cards did not change when you received the sorting rule. They were always lying exactly as they were dealt. What changed was your ability to see the order that was hiding inside an arrangement that looked random. The delayed choice does not deal the cards again. It only hands you late, the rule for reading a deal that was already complete. The signal photons landed where they landed. The later choice never moves a single one. It only decides whether you possess the key that reveals the order or the key that reveals the disorder. And both keys were always going to come from the same already finished reality. So, why does it still haunt people, even stated correctly? It haunts us because of what it says about when the photon was a wave or a particle. We cannot point to any moment and say, here, at the slits, the photon decided to be one or the other, because the information that determines which description fits was still locked inside an entangled partner photon that had not yet met its fate. The wave nature and the particle nature were not properties the signal photon carried at the slits, settled and stored, waiting to be read out. They were features of the entire entangled situation, the signal and the idler together, a situation not resolved until the very last piece of it played out, possibly long after the signal photon was already a fixed dot on a screen. The photon was never simply a wave or simply a particle at any single place or time. The whole arrangement, stretched across space and across the long delay, behaved as one indivisible thing, and the question of what the photon was has no answer that lives at any single moment inside it. This is the midnight of our story, so let the dread sit here a while. We have learned that the wave behavior of a particle is tied not to the particle alone, but to whether information about it exists anywhere in the universe, including inside a second particle that has flown light seconds away, including in a record not yet read, including in an outcome not yet determined. We have learned that the world will rearrange what patterns we are able to see in order to keep this rule unbroken. We have learned that there is no moment we can point to and say, here, this is where the photon decided. The deciding is smeared across the entire entangled situation, refusing to live at any single point in space or time. And there is a final twist of the knife in this part, one that closes the door on the last easy escape. You might think you could outrun the bookkeeping by being clever about distance, send the idler photon light years away before deciding to read it or erase it. Surely, you think, the signal photon back home must commit to something definite in the meantime. It cannot wait around for a partner crawling across the galaxy, but the consistency holds across any distance you like. The connection that keeps the books balanced does not weaken with separation, does not care how far the entangled partners have drifted, does not respect the comfortable idea that distant things lead separate lives. This is the non-local heart of entanglement, and it is the thing Einstein could not abide. Whatever binds the signal and the idler into a single situation is not a force passing between them, not a signal racing from one to the other, because no signal could keep up across such distances, and no signal is ever found. It is something more unsettling than a force. It is the plain refusal of the two particles to be two separate realities at all. They are one thing wearing the disguise of two, and the disguise does not slip no matter how far apart you pull them. And so the bookkeeping is not local bookkeeping. It is not as though each particle keeps its own private ledger and the ledgers happen to agree. There is one ledger for the whole entangled situation, a single accounting that spans the entire arrangement at once, across the room, across the delay, across the light years, and that single ledger is what never, ever shows a contradiction. The universe does not balance its books, particle by particle and place by place. It balances them all at once, as a whole, in a way that makes the very idea of separate local pieces start to dissolve in your hands. That dissolving is the thing to carry forward. The deeper we push, the less the world looks like a collection of separate things in separate places, and the more it looks like one connected fabric that only appears, at our scale, to be cut into independent parts. And we still have not answered the question underneath all of it. We have only made it sharper and colder. When the photon's path becomes knowable, the wave goes away. When does knowable become known? What physical event, exactly, converts a shimmer of overlapping possibility into a single fact about the world? The detector that reads the idler is itself made of atoms in superposition. The erasing maze is made of atoms in superposition. Where, in this chain of quantum pieces touching quantum pieces, does anything ever actually become definite? We have circled the measurement problem from the outside, watched it bend space and toy with time. In the next part, we go straight into its center. We are going to look at the equation that governs all of this, the most successful equation ever written, and we are going to find that it contains nowhere within it any instruction for when a possibility becomes a fact. The theory that predicts everything tells us nothing about the one thing we most want to know. Keep the wall in your mind. Keep the two patterns, the bands and the stripes. We are going to ask what looking really is, and we are going to find that the equation does not know either. Let us go to the equation. I promise not to write any mathematics on the screen, but I want you to feel the shape of what it does, because the whole mystery lives in a contradiction between two things the theory says. And once you see the contradiction clearly, you can never unsee it. At the heart of quantum mechanics is a rule for how the wave function changes over time. It is called the Schrödinger equation, and it is one of the great triumphs of the human mind. Give it the wave function of a system right now, and it tells you exactly what that wave function will be a moment from now and a moment after that, smoothly, continuously, with perfect precision. It has never been found wrong. Every prediction it makes, checked to more decimal places than almost anything else in science, comes out right. When physicists say quantum mechanics is the most accurately tested theory in history, this equation is the engine doing the predicting. And here is the first thing to understand about it. The Schrödinger equation is completely smooth and completely deterministic. There are no jumps in it. There is no randomness in it. It describes the wave function flowing and spreading and evolving like a perfectly predictable fluid. If the electron is in a superposition of going through both slits, the equation keeps it in that superposition and evolves it forward gracefully. Nothing in the equation ever forces the electron to choose. Nothing in it ever collapses the possibilities down to one. The equation, left to itself, would keep every possibility alive forever, smoothly interfering, never deciding. Now hold that beside what actually happens when we measure. When the electron hits the screen, it does not land smeared across every possible position in proportion to its wave. It lands in one place, one dot, one definite outcome out of all the possibilities the wave function held, and the choice of which place appears to be genuinely random, governed only by probabilities the wave function assigns. A possibility became a fact. A spread became a point. The shimmer became a single definite thing. So we have two rules, and they do not fit together. Rule 1, the Schrödinger equation, smooth and deterministic, keeps all possibilities alive and never picks. Rule 2, what we see in every measurement, sudden and random, picks exactly one outcome and throws the rest away. The theory as it is actually used by physicists every day contains both rules bolted together. We let the wave function evolve smoothly by the equation right up until a measurement, and then, by hand, we switch to the other rule and say, now it collapses to one outcome, with these probabilities. We even have a name for the second rule, the collapse of the wave function, the sudden jump from many to one. But here is the wound at the center of physics. The equation never tells you when to switch rules. Nowhere in the mathematics is there a line that says, a measurement is occurring now, stop evolving smoothly and collapse. We insert that switch ourselves, by intuition, by convention, by knowing roughly when an experiment counts as finished. The theory does not define measurement. It does not tell us what physical process constitutes one. It does not tell us what is special about a detector that a single atom does not have. The most precise theory ever built has, at its very core, an undefined word that we paper over with common sense. That undefined word is measurement, and the gap it leaves is the measurement problem. Let me sharpen the knife. Everything is made of quantum stuff. The electron is quantum. The detector is a great pile of atoms, and every one of them is quantum, governed by the same Schrödinger equation. The hard drive that stores the result is quantum. The air in the room is quantum. Your eye is quantum. The neurons in your brain are quantum. There is no special non-quantum material in the universe that we have ever found, no magic classical substance exempt from the equation. So, in principle, we should be able to write one giant wave function for the electron and the detector and the room and you all evolving together smoothly by the equation, never collapsing. And if we do that, the equation gives an answer that is honest and horrifying. It says the detector itself goes into a superposition. The pointer that is supposed to read left and the pointer that is supposed to read right both happen, woven together, just like the two slits. The equation does not collapse the detector any more than it collapsed the electron. It entangles them. Now you have a detector that registered both outcomes at once. And if you walk in and look, the equation says you become part of the superposition too. There is a version of you that saw left, and a version of you that saw right, both real in the mathematics, both evolving smoothly forward. The equation never produces a single you seeing a single result. It produces a branching tree of every possibility, all coexisting, but that is not what you experience. You experience one result. You see the pointer at left, or you see it at right. Never both, never a blur, never a branching ghost of yourself. So either the equation is wrong somewhere, or it is incomplete somewhere, or there is something profound about the relationship between the smooth mathematics and the single world you actually live in that we do not understand. That gap between the many possibilities the equation insists on and the single outcome you always observe is the whole problem, stated as plainly as it can be stated. Now, I have to be fair, because there is a piece of real progress here, and it is important, and it is also widely oversold, so let me give it to you straight. The piece of progress is called decoherence, and it is genuine physics, fully worked out, not controversial. Here is what it says. When a quantum system in superposition touches a large, messy environment, the air, the detector, the warmth of the room, the countless particles around it, the superposition does not stay neatly contained. It leaks. The two strands of possibility get entangled not just with a detector, but with billions upon billions of surrounding particles, spreading the quantum information out into the environment so thoroughly and so fast that it becomes utterly impossible to gather it back. And once that information is spread, the two possibilities can no longer interfere with each other. The stripes become unobservable. The wave behavior vanishes for all practical purposes. Decoherence explains beautifully and quantitatively why we never see big objects in obvious superpositions, why a chair is never visibly in two places, why the wave-like character of things drowns the instant they interact with a warm, busy world. It explains why the boundary between quantum and classical looks the way it looks. It tells us why interference is so fragile and why the everyday world looks solid and definite. That is real and it matters. But now I have to tell you what decoherence does not do, because this is exactly where the oversold version lies to you. Decoherence explains why the possibilities stop interfering and become separate, non-overlapping branches. It does not explain why only one of those branches becomes your reality. It turns the neat superposition into a set of distinct possibilities that no longer talk to each other, the detector reading left in one, reading right in the other. But both branches are still there in the mathematics. Decoherence never deletes a branch. It never picks a winner. It explains why the branches stop interfering, not why you only ever find yourself in one of them. So the hard core of the problem survives untouched. We still have a smooth equation that produces a branching tree of coexisting outcomes, and we still have your stubborn experience of a single result, and decoherence, for all its genuine power, builds the most beautiful bridge right up to the edge of that chasm, and then stops, because the last step from many real branches to one experienced world is not in the equation. Nobody has put it in the equation. Perhaps it does not belong in the equation. That is precisely what the disagreement is about. And notice what we have arrived at. We have a theory that works perfectly, not approximately, perfectly, as far as any experiment can measure. It predicts the patterns on the screen, the probabilities, the timings, the spectra of atoms, the behavior of every quantum device humanity has ever built. The chip in the machine you are watching me on right now. It is flawless as a tool, and it is silent on the one question a curious person most wants answered. What is actually happening when the possibilities become a fact? What occurs? Where is the line? What is a measurement? The theory shrugs. It hands you the right numbers and refuses to tell you what they mean. Let me name the precise property of the equation that causes all this, because it makes the trouble feel less like a mystery and more like an honest consequence we cannot wriggle out of. The Schrödinger equation is linear. That is a technical word, but the meaning is simple and merciless. If the equation allows one possibility to evolve in a certain way and allows a second possibility to evolve in a certain way, then it absolutely requires that a combination of the two possibilities evolves as the combination of those evolutions. The math has no choice. If the electron going left is allowed and the electron going right is allowed, then the electron going both, the superposition, is not just permitted but mandatory as a valid state, and it must keep evolving as both. Linearity is why superpositions cannot simply decay away on their own inside the pure equation. The equation, by its very structure, preserves the both. It carries the both forward faithfully into the detector, into the room, into you. The branching is not a strange add-on. It is the equation doing exactly and only what a linear equation must do, which means that getting a single outcome out at the end is not a small adjustment. It is a violation of the equation's deepest structural habit, and that is precisely why no one can find a way to make a single outcome emerge from the equation alone. So the silence of the theory is not laziness or an oversight that a sharper graduate student will patch next year. It is structural. The equation is built in a way that conserves possibility, and the world we experience is built in a way that destroys all possibilities but one, and those two facts grind against each other at the foundation. Every attempt to resolve the grinding either changes the equation or denies that possibilities are really destroyed, or refuses to discuss what happens between measurements at all. There is no fourth door that everyone has simply overlooked. The grinding is the problem, and it is honest, and it is old, and it is still turning. That is a deeply strange situation to be in, and I want you to feel how strange it is. Imagine owning a map that guided you flawlessly to every destination you ever sought, never once leading you wrong, and yet the map, when you studied it closely, did not seem to depict any territory you could recognize, and the map makers themselves, the most brilliant people alive, fell into bitter disagreement about what the map was a map of. That is quantum mechanics. The directions are perfect. The picture of the world behind the directions is missing, or contested, or possibly unknowable. There is a famous way of feeling the absurdity of this, and you have probably heard its name without hearing the point. A physicist named Erwin Schrödinger, the same man whose equation we have been discussing, invented a thought experiment to show how ridiculous the situation becomes when you take the equation literally and let the superposition grow. He imagined a cat sealed in a box with a single radioactive atom, a quantum thing, in a superposition of having decayed and not decayed. If it decays, a mechanism releases a poison and the cat dies. If it does not, the cat lives. Now, the atom is in a superposition of both. So by the equation, with nothing to collapse it, the whole contraption evolves into a superposition too, and the cat becomes a blend of alive and dead, both at once, woven together until someone opens the box. Schrödinger did not propose this because he thought cats were really both alive and dead. He proposed it as a protest. He was pointing at the equation and saying, "Look where this leads if you take it seriously, and never tell me when the collapse happens." The cat is just the electron writ large. There is no clear line in the mathematics that says the strangeness is allowed for the atom but forbidden for the cat. If the atom can be both, and the cat is made of atoms, and the equation never collapses anything, then the equation says the cat is both, and that is plainly absurd, and the absurdity is the whole point. The cat in the box is the measurement problem wearing fur. It dramatizes the exact gap we have been circling, somewhere between the atom and the cat, between the one particle and the great pile of them. The shimmer is supposed to become a fact, and the theory will not tell us where, or how, or why. And notice that decoherence, real and powerful as it is, does not rescue the cat. Decoherence tells you that the alive branch and the dead branch stop interfering almost instantly, because a cat is a warm, wet object entangled with trillions of particles, so you would never, ever see the two versions overlap and produce some ghostly interference of living and dead. Good. That explains why the cat looks definite. But decoherence still leaves both branches in the mathematics. It gives you a clean alive cat and a clean dead cat, no longer blurred together, but still both present, still both in the equation, and it never tells you why you open the box and find only one of them. The two branches are perfectly separated and perfectly real, and the question of why your reality contains just one of them is exactly as unanswered as before. The bridge is built right up to the chasm, and the last step is not there. Where does that leave us? It leaves us facing a fork, and down each path of the fork lies a different story about what is really going on, a different answer to the question of what a measurement is and why you only ever see one world. Some say the collapse is real, and we just have not finished the physics that describes it. Some say there is no collapse at all, and every branch is equally real, every outcome happening in its own world. Some say the wave function was never a real thing in the first place, only a catalogue of our knowledge. Some say there is a hidden layer of reality underneath, definite all along, that the equation simply fails to show us. Each of these is a serious proposal held by serious physicists. Each one swallows a different bitter pill. And here is the part that should unsettle you most of all, the part we turn to next. Every one of these wildly different stories about the nature of reality predicts exactly the same results for every experiment we know how to do. The screen looks the same in all of them. The data cannot tell them apart. We are not arguing about the facts. We are arguing about what the facts are made of. Keep the wall in your mind. Keep the smooth equation and the single dot it cannot explain. We are about to meet the rival stories and discover that reality itself has become a matter on which the experts simply, profoundly disagree. We have arrived at the strangest crossroads in all of science. One set of equations, perfect in its predictions, and several completely different stories about what those equations mean. Let me lay the stories out for you, one at a time, fairly, each with its real strength and its real cost. I am not going to tell you which is true, because nobody knows which is true, and anyone who tells you they are certain is selling you something. But I want you to see the shape of the disagreement, because the disagreement itself is the lesson. Start with the oldest story, the one most of us were taught without ever being told it was a choice. It is called the Copenhagen interpretation, after the city where Niels Bohr did much of his thinking. The Copenhagen view says, in essence, do not ask what the electron is doing when no one is measuring it. The wave function is a tool for predicting the probabilities of measurement outcomes, and measurement is where physics speaks. Before measurement, the question of where the electron really is has no answer, not because we are ignorant, but because there is no fact of the matter. The act of measurement brings a definite property into being. The collapse is real, and it happens at measurement, and we should not expect the theory to describe a world existing independently of observation. The strength of Copenhagen is its discipline. It refuses to invent unobservable machinery. It sticks to what you can actually measure and makes no claims it cannot back with data. For decades, it let physicists get on with their work without being paralyzed by metaphysics. Calculate, predict, measure, move on. It is honest about the limits of what we can say. But the cost is severe, and it is the cost we spent the whole last part uncovering. Copenhagen draws a line between the quantum system and the classical measuring apparatus, and it never tells you where that line is, or what physical thing constitutes a measurement. It treats measurement as a fundamental, unanalyzed act, even though the measuring device is itself made of quantum particles. It puts the observer in a special role without ever defining what qualifies as an observer or why a hard drive should count or not count. Push on it, and it dissolves into vagueness, exactly where you most want clarity. Many physicists today find this an evasion dressed as wisdom, a refusal to answer the question rather than an answer. So consider the opposite extreme. A story that pays any price to keep the equation clean. It is called the many worlds interpretation, and it begins with a single radical act of honesty. It says, take the Schrödinger equation completely seriously and never add anything to it. No collapse, no special measurement, no line between quantum and classical. The equation says the detector goes into superposition, so the detector really goes into superposition. The equation says you branch into a version that saw left and a version that saw right, so you really branch. Both outcomes happen. Both are equally real. The universe splits constantly into an unimaginable multitude of branches, one for every possible outcome of every quantum event, and you experience only one branch because there is now a copy of you in each, and each copy sees a single definite world. The strength of many worlds is breathtaking simplicity at the level of the law. It is the only interpretation that needs just one rule, the smooth equation, and nothing else. No mysterious collapse. No undefined measurement, no special observers. The interference, the eraser, the single dot, all of it follows from the equation taken literally. The reason you see one outcome is simply that you are one of the branches. Nothing was ever added. The measurement problem dissolves because there is no collapse to explain. But feel the price. To keep the equation pure, many worlds asks you to believe in a staggering, ceaseless proliferation of entire universes, almost all of them forever inaccessible to you, containing countless copies of yourself, living out every outcome you did not see. Every time anything quantum happens, and that is everywhere, always, the world multiplies. The theory buys mathematical elegance with an ontological extravagance that many find impossible to swallow, and it has its own technical thorn. If everything happens, what does it even mean to say one outcome is more probable than another? Making ordinary probability make sense inside a theory where every outcome certainly occurs is a genuine unsolved difficulty that its defenders are still wrestling with. Elegant law, unfathomable world. That is the bargain. Now take a third path, one that keeps a single world but changes the physics to do it. These are the objective collapse theories. They say the collapse is real, just as Copenhagen claims, but it is not triggered by observation or measurement at all. It is a physical process built into nature, happening on its own, all the time, everywhere, governed by a new ingredient added to the equation. In these theories, the wave function occasionally, spontaneously, collapses on its own, with a probability that grows with the size of the system. For a single electron, collapse almost never happens, so it stays in superposition and interferes freely. For a detector made of trillions of particles, collapse happens so fast and so reliably that it is essentially instantaneous, which is why big things always have definite positions and never visibly shimmer. The line between quantum and classical is not put in by hand. It emerges naturally from the size of the system. The strength of objective collapse is that it actually answers the question. It says precisely what a measurement is. A measurement is when enough particles get involved that spontaneous collapse becomes overwhelmingly likely. No observers, no consciousness, no vague boundary. A definite physical mechanism, the same one, from the electron to the detector to you, and it has a second virtue that the others lack. Because it changes the equation, it makes predictions that differ very slightly from standard quantum mechanics in extreme conditions. It can, in principle, be tested. Experiments are being built right now to look for the tiny extra wobble these theories predict. This is real science with a real way to be proven wrong. But the cost is real too. Objective collapse adds new constants to nature, new ingredients, tuned just so to match what we see. And so far no experiment has detected the deviations they require, which steadily squeezes the space they can live in. It is a more complicated theory than the bare equation, and it risks being an elaborate fix for a problem that might have a simpler resolution. Still, of all the stories, it is the one most willing to put itself in front of an experiment and risk its own neck, and there is something deeply admirable in that. There is a fourth path I will give you more briefly, because it shows that even our sense of randomness might be optional. It is the pilot wave picture, sometimes called the de Broglie-Bohm theory. It says the particle is always a real particle, with a definite position at every moment, a genuine marble after all. But it is guided by a real wave that fills space and flows through both slits, steering the particle along. The particle goes through one slit, but the wave goes through both, and the wave pushes the particle into the interference pattern. Nothing is ever in two places. There is no collapse. The apparent randomness of where the electron lands comes only from our ignorance of its exact starting position, not from any true dice in nature. Everything is determined, definite, and clockwork underneath. The strength of pilot wave is that it gives you back a clear, definite world with particles that have positions and paths, the kind of reality our intuition craves, and it reproduces every quantum prediction exactly. The cost is that the guiding wave must reach across all of space instantaneously, coordinating distant particles in a way that sits uneasily with relativity and the theory has never extended as cleanly to the full quantum picture of fields and forces as its rivals. Still, it is a living counterexample to the claim that quantum mechanics forces us to give up a definite reality. It proves we are choosing to, not being forced to. Before we step back, I owe you the story of how we know that some of the easiest escape routes are closed, because it is one of the most beautiful results in all of physics, and it tells you this is real science, not just talk. Remember Einstein's hope that the electron secretly carries definite properties all along, and the randomness is only our ignorance of a hidden layer. For 30 years that sounded like a matter of taste, untestable, a thing you could believe or not believe without consequence. Then a physicist named John Bell found something extraordinary. He proved that if there really were such a hidden layer, a layer where every particle carried definite local properties decided in advance, then certain measurements on entangled pairs would have to obey a precise numerical limit, a ceiling, a line that no theory of definite local hidden properties could ever cross. And quantum mechanics predicted that the real world would cross it. So the philosophical question became an experiment with a yes or no answer. People built the apparatus. They measured entangled pairs, thousands, and then millions of them, closing loophole after loophole over decades, tightening the test until there was nowhere left to hide, and the world crossed the line every time. The limit that any locally definite hidden layer would have to respect is violated by nature, exactly as quantum mechanics said it would be. The comforting picture, the one where particles quietly carry all their answers in advance and we are merely ignorant, cannot be true, at least not without giving up the idea that distant things have separate, independent realities. This was honored with the highest recognition in physics, and rightly, because it took the deepest question we have and forced nature to answer part of it out loud. The strangeness is not a gap in our knowledge that a cleverer classical picture will someday fill. It is a feature of the world confirmed that any acceptable story now has to swallow whole. That is why the interpretations we just walked through are so radical. They are radical because the gentle options are dead. You cannot keep a world of separate, definite, locally real little particles and also match what the laboratory shows. Something precious has to be given up. Copenhagen gives up the idea that there is any describable reality between measurements. Many worlds gives up the idea that there is a single world. Objective collapse gives up the pure equation and adds new physics. Pilot wave keeps definite particles, but gives up the idea that distant things are independent, letting its guiding wave coordinate the whole universe at once. Every survivor on the menu pays a price that would have horrified a physicist of an earlier age, and they pay it because Bell and the experiments that followed proved that the cheap options are not available. There is no free version of reality left to buy. Now, step back and look at what we have. 4 stories. Collapse is real and tied to measurement. Every outcome is real in its own world. Collapse is real and physical and sizes itself by the number of particles. The particle was definite all along, and a hidden wave steered it. These are not small differences. They disagree about whether other worlds exist, about whether the future is determined, about whether the wave function is a real physical thing or just a ledger of our knowledge, about whether reality is one or many. They disagree about the deepest possible questions. And here is the fact that should make the hair stand up on your arms. For everything we currently know how to measure, all of these stories predict exactly the same results. The screen shows the same stripes. The detector clicks at the same rate. The probabilities come out identical to the last decimal. Apart from objective collapse, which holds out the slender hope of a future test, no experiment we can perform today can tell these pictures apart. We are not waiting on better data about what the electron does. We have the data. We have had it for a century. We are waiting, perhaps forever, for a way to decide what the data are telling us about the nature of what exists. There is a fifth family of views I have held back, lighter than the others but worth a breath, because it shows how deep the disagreement reaches. Some physicists have come to suspect that the wave function was never a description of the world at all, but a description of an observer's information about the world. On this view, the collapse is not a physical event out there. It is simply what happens to your knowledge when you learn a result. The way the odds on a coin snap from a spread to a certainty the instant you see how it landed. Nothing physical jumps, only your information updates. Reality, on these views, may not have a single observer, independent state at all, and the whole search for what is really happening behind the wave function may be a search for something that was never there. It is an elegant dissolving of the problem, and to its critics it is a quiet surrender, a refusal to say anything about the world itself, only about our bets on it. But it is held seriously by serious people, and that is the point I keep returning to. Even the question of whether the wave function is a thing in the world or a thought in your head divides the experts, and the divisions are not quietly narrowing toward a winner with each passing decade, which is what you might expect from a healthy scientific question. When physicists are surveyed about which interpretation they favor, no single view commands a majority, and the results shift from pole to pole and from room to room. A gathering of specialists will split, sometimes almost evenly, across Copenhagen and many worlds and the rest, and the same person will sometimes give a different answer in a different year. This is not how settled science behaves. It is how a genuinely open foundational question behaves. 100 years in, the community that understands this theory better than anyone has not converged. They have learned to use the theory in perfect unison and to disagree profoundly and permanently about what they are using. That is the philosophical core of this whole journey, and it is worth saying as plainly as I can. This is not ignorance of the facts. The facts are settled and reproduced in every laboratory on Earth. This is a disagreement about what reality is, underneath facts that everyone agrees on. The most successful theory in the history of human thought works flawlessly and comes with a menu of mutually contradictory descriptions of the world, and the people who understand it best cannot agree which description is true, and the universe, so far, declines to tell us. Recent surveys of physicists find no majority for any single view. A century in, the house is still divided. We have widened as far as the question goes. We have gone from a wall with 2 slits all the way out to the boundary of what can be known about the nature of existence, and found the experts standing there in the dark, holding the same perfect equation, telling different stories about the same shadows on the same screen. In the final part, we are going to come back down, back from the metaphysics, back to the human scale, back to the wall and the 2 slits, and the single quiet dot. And we are going to ask what it means to live inside a question this deep, and whether there is, in the not knowing, something other than dread. Keep the wall in your mind. We are almost home. Let us come back down now. Back from the branching worlds and the spontaneous collapses and the guiding waves. Back to a person sitting in a room, which is where you are and where I am, and where every physicist who ever wrestled with this also sat. Let the cosmic scale fall away for a moment, and let us be human about what we have found. Here is the plain truth we have to hold. We possess the most precisely tested theory in the history of our species. Quantum mechanics has been confirmed to a staggering number of decimal places. It underlies the transistor and therefore every computer and every phone. It explains why the sun shines, why atoms hold together, why chemistry works, why the world has the textures and colors and solidity it has. As a set of instructions for predicting what nature will do, it has never once failed, not once. And after 100 years of using it flawlessly, we still cannot agree on what it says about reality. We do not know what a measurement is. We do not know whether the wave function is a real thing in the world or a summary of our knowledge. We do not know whether the other outcomes happen somewhere else or simply never happen at all. We hold the perfect instrument and we cannot read the meaning off its face. Sit with how unusual that is, because nothing else in our experience is like it. We are used to understanding growing alongside accuracy. We expect that if we can predict something perfectly, we must understand it deeply. Quantum mechanics breaks that expectation in two. It is the place where prediction and understanding came apart, where we learn to forecast the behavior of reality with surgical precision while remaining genuinely unsure what reality is. It is humbling in a way that little else is. The smartest people who have ever lived built this thing, use it every day, and stand before its central question as uncertain as children. Now, let me take you back to the wall. Remember it, the flat barrier, the two narrow openings side by side, the screen behind. We have carried it through this entire journey, and I want you to look at it one more time, now that you know what you know. When we started, it was almost insultingly simple. A child could build it. It looked like nothing. And now, after everything, look at what that humble object actually is. It is the smallest possible window onto the deepest crack in our understanding of existence. Every strangeness we have explored, the self-interference, the vanishing wave, the eraser that toys with time, the branching equation, the warring interpretations, all of it pours out of that one small wall with two openings. The simplest experiment you can imagine contains the single hardest question we have ever asked. And here is what I find when I sit with that instead of dread. I want to offer it to you not as an answer, because I have none, but as a way to hold the question. We went looking, all of us, for a universe that would behave itself, a universe of little marbles with definite positions, doing definite things, whether or not anyone watched. We wanted reality to be furniture, solid and indifferent, sitting there the same way when the lights are off. And the wall with two slits told us, gently and unmistakably, that it is not like that. That at its foundation the world is woven from possibility, from overlapping might be and could be, and that the definite, solid world we live in is something that comes into focus out of that shimmer, rather than something that was simply lying there all along. That is not a comfortable answer, but notice that it is not an empty one either. It is a real discovery about the texture of existence, paid for in honest experiment, and we are among the first generations of humans ever to know it. I think it is worth pausing on why this particular not knowing feels so different from the ordinary gaps in human knowledge, because naming the difference is part of making peace with it. There are things we do not know yet but expect to learn, like the cure for some disease or the depth of some ocean trench, and those gaps feel like work waiting to be done. The measurement problem is not that kind of gap. It is not that we are missing a measurement. We have all the measurements. We can predict every one of them. What we are missing is an agreement about what the successful predictions are describing, and that is a stranger and more permanent kind of unknown, because it is not clear that any future experiment could settle it. 3 of our 4 stories give identical predictions for everything we can test. You cannot measure your way out of a disagreement that lives entirely beneath the level of measurement. We may be looking at a question that is real and meaningful, and yet forever out of reach of the only tool, experiment, that we trust to decide such things. That is a vertigo of a special kind. It is the vertigo of standing at the exact edge of what the scientific method can reach, and seeing that the edge is not at the limit of our instruments, but somewhere deeper, woven into the relationship between mathematics and meaning itself. And yet I do not think this should curdle into despair, and here is why. Look at how much we did learn on the way to this edge. We learned that the divide between particle and wave is not fundamental. We learned that information and reality are bound together far more tightly than anyone suspected, that whether a thing behaves as a wave depends on whether an answer about it exists anywhere in the world. We learned through Bell and the experiments that followed that nature cannot be both local and definite in the comfortable old way, and that this is not opinion but tested fact. We learned to build technologies on top of all this strangeness. Quantum computers that compute by keeping possibilities alive and interfering on purpose. Encryption that is secure because of the very impossibility of secretly reading a quantum state. The mystery at the center did not stop the progress around it. We have been building a cathedral around a locked room, and the cathedral is magnificent and useful and true, even though the door at its heart has never opened. The not knowing sits inside an enormous amount of knowing. It is not a darkness with nothing in it. It is a single dark window in a vast lit house that we built ourselves, brick by tested brick. There is a strange intimacy in that, if you let yourself feel it. The same equations that govern the photon arriving from a distant star govern the electron in the screen in front of you and the atoms in the hand you are holding it with. You are not separate from this mystery, watching it from outside. You are made of the very stuff that refuses to be pinned down, the same superpositions, the same entanglements, the same impossible duality, all of it humming away inside every cell of you right now, decohering too fast and too thoroughly for you to ever feel it, but there, underneath, the whole time. The mystery is not far away in a laboratory. It is what you are, and maybe that reframes the not knowing. We tend to treat an unanswered question as a kind of failure, a debt to be paid off, a gap to be closed and forgotten. But some questions are not gaps. Some questions are rooms you get to live inside. The measurement problem has been open for 100 years, not because we are stupid, but because it sits exactly at the place where our oldest intuitions about what the world is run out of road. To stand at that place, awake, honest, without reaching for a comforting story you have not earned, is not ignorance. It is a rare and difficult kind of seeing. The physicists who refuse the easy answers and keep the question open are not confused. They are being faithful to how strange the truth actually is. Consider, too, what it asks of us as people to live well with a question this size. We are a species that hungers for closure. We want the box opened, the answer named, the mystery filed away so we can sleep. Almost every story we tell ourselves, from the smallest gossip to the grandest myth, is built to resolve, to land on a final note, to tell us how it all comes out. And here is one of the deepest features of the world we have ever uncovered, sitting open, unresolved, after the labor of the most careful minds across 100 years, and it simply will not land. To hold that without flinching, without grabbing the nearest comforting story and calling it truth, without pretending to a certainty you have not earned, is a discipline. It is the same discipline the best physicists practice when they say, "Honestly, we do not know what a measurement is." There is a kind of courage in that sentence. It would be easier to pick a side and defend it with the heat of belief. It is harder and finer to keep the question open in the exact shape the evidence demands, no larger and no smaller, and to let it stay open as long as honesty requires. And maybe there is even a quiet gift buried in it. A world that had given up all its secrets would be a smaller world to live in. The fact that reality, examined at its foundation, turns out to be stranger and less settled than we assumed, means that the universe is still capable of astonishing us, still has depths we have not touched, still holds a room we have not entered. Every time you look at something solid and ordinary now, you can know that underneath its calm surface lies this shimmer of unresolved possibility, this open question that the cleverest people alive cannot close. The world is not the flat, finished, fully explained machine we sometimes fear it has become. It is still mysterious in its bones, mysterious in a way that is real and earned and pointed to by hard evidence, not by wishful thinking. There are not many genuine mysteries left that are both this deep and this honest. We are lucky, in a strange way, to have one. So I am not going to give you a tidy resolution, because the honest thing, the thing this whole video has been built to protect, is that there is not one yet. The universe does not behave differently because it knows you are looking. That was always the cheap version, and we set it aside in the very first minutes. The real situation is quieter and far stranger. Reality keeps a perfect, seamless consistency about what can be known, and in keeping it, it declines to be either the wave or the particle, the here or the there, the this or the that, until the world itself records an answer. And the moment of that recording, the act we keep calling measurement, the hinge on which a possibility becomes a fact, remains, after a century of the finest minds we have, undefined, not unmeasured. Undefined. We do not have the words for it yet, and we are honest enough to admit we do not. Let that land, one last time. The wall is still there. The electron is still in flight, somehow exploring both paths at once, the way it has on every screen in every lab for 100 years. And the deepest thing we can say about that small, patient, ongoing fact is that we do not fully understand it, and that our not understanding is not a wall but a window, open onto a reality far richer and far less furniture-like than the one we expected to find. When I really let this settle, what stays with me is not the dread and not even the wonder, but a kind of tenderness toward the whole human effort it represents. Think of the chain of people who built this understanding. Young with his candle and his slits. Newton wrong in the most productive way a person can be wrong. Bohr and Einstein arguing for decades, neither able to defeat the other, both made larger by the fight. Schrödinger writing his equation and then recoiling from where it led, inventing his poor imaginary cat to show how strange his own creation was. Bell quietly turning the deepest question of all into something a laboratory could test. And the unnamed thousands since, refining the experiments, closing the loopholes, building the machines, keeping the question honest. None of them got to see the answer. Every one of them handed the open question forward, a little sharper, a little clearer, to the people who came next. That is what understanding actually looks like up close. Not a single triumphant moment of revelation, but a long relay of careful, humble people passing a lit question hand to hand across the centuries, each one refusing to pretend it was solved. And now, it has been handed to you, not the answer, the question, which is, in the end, the more valuable inheritance, because answers close and questions open. You can walk back into your ordinary day, the dishes and the traffic and the small concerns, carrying this. You can look at the solid world and know that its solidity is a kind of achievement, something that comes into focus out of a deeper shimmer, rather than a brute given. You do not have to resolve it. You are not required to pick a side or pretend a certainty. You are only invited to know that the question is there, real and open and beautiful, underneath the surface of everything, including you. That knowing changes nothing about how you live, and everything about how the world feels while you live in it. The table is still a table, but now you know what a strange and wonderful thing it is that it manages to stay one. That is enough. That is, I think, more than enough. To know the world this precisely, and to be this honestly unsure of what it is, at the same time, in the same mind, without flinching toward false comfort, is its own quiet form of understanding, the kind that does not close the question but learns, slowly, to be at home inside it. Thank you for sitting with something difficult all the way to the end. If this gave you that particular feeling, the one where the floor of the ordinary world gets a little thinner and you can sense the strangeness pressing up through it, then stay a while. There are more of these waiting for you, more simple objects hiding impossible questions, and I would be glad to walk into the next one beside you. Until then, look at the solid world around you, the table, the wall, your own steady hands, and remember what it is quietly made of, and rest well wherever you are, whatever time it has become while we sat here together at the edge of the question.